Hey everyone, welcome to BCP Med. In this video, we're going to be taking a look at atomic and ionic radii and the periodic trends associated with them. We're going to be seeing how effective nuclear charge and the energy levels impact the size of an atom, how cation and anion radiuses differ from that of a neutral atom, and make some comparisons of different salts to see just how different the size of cations and anions really are. Let's go ahead and get started. So it is a pretty easily observed trend that atomic radius tends to increase as you move vertically down a group in the periodic table, right? So the top of the periodic table is going to contain relatively small atoms, whereas the bottom is going to contain relatively large atoms. But why is this the case? Well, electrons are restricted to certain orbits by energy levels, the quantum number n, which increase in distance from the nucleus, right? Each successive energy level is going to be a further radius from the nucleus, as shown by this model here. In fact, they sort of look like Russian nesting dolls, where each successive energy level is enveloping the energy levels below it at a larger radius. And so each new row on the periodic table, each period, represents a new energy level and is therefore further from the nucleus than the period above it. So every time a new energy level is started, R is going to increase significantly. For example, let's go ahead and look at the alkali metals to understand just how much is changing. We see that the radius from lithium to sodium increases from 167 to 190 picometers, and then from 190 to 243, then to 265, and then to 343 with from rubidium to cesium. So we see clearly there's a large increase in radius every time that we go down one row in the periodic table. The other trend associated with atomic radius is going across a row, and that is that the radius tends to decrease substantially across a period, right? So the atoms on the left-hand side of the periodic table are going to be rather large, right? Those alkali metals and alkali earth metals are quite large, whereas the non-metals on the right-hand side are going to be quite small. Why is this the case? Well, it turns out that the effective nuclear charge is also increasing towards the right-hand side of the periodic table. And as effective nuclear charge increases, the nucleus is going to pull harder on those valence electrons and pull them closer. So if we have an atom with an effective nuclear charge of +2, like say beryllium, it's not going to pull very hard on its valence electrons. So they're going to be relatively far away. Whereas if we have an atom like neon with +8 effective nuclear charge, it is going to pull very hard on those valence electrons and shrink the size of the electron cloud. So if we look at the period 2 elements, starting from boron, we'll see that the radius collapses very quickly from 87 picometers all the way down to 38 picometers at neon. So as effective nuclear charge increases towards the right, the atomic radius collapses as the nucleus pulls harder and harder on the electron cloud. One of the best ways to visualize the trends in atomic radius is to look at a graph of radius versus atomic number. The vertical spikes that you see on this graph here correspond to the creation of a new energy level. As you notice, each new energy level leads to a substantial increase in the atomic radius, and overall, as the atomic number increases towards the right, the radius tends to increase as well. There is a positive linear correlation between atomic number and radius. However, in between, there's a lot of changes. In fact, between peaks, there's a downward slope of the graph every time before a new energy level is created, and that is due to the effective nuclear charge increase. The top of the peak corresponds to alkali metals with low effective nuclear charges of +1, and the bottoms are the noble gases with effective nuclear charges of +8, as per our simple approximation. And so the radius decreases with effective nuclear charge, spikes with an increase in energy level, and then again decreases with the increase in effective nuclear charge. Pretty straightforward. Now, ionic radii are a bit more complicated than that of neutral atoms. It is always the case that a positive ion is going to be smaller than a neutral atom. Why is that the case? Well, there's two effects to consider. The first one is a bit more straightforward, and that's, well, that a net positive charge is simply going to pull harder on the electron cloud because it has a stronger Coulomb attraction to those electrons, and it's going to shrink the radius, right? It turns out that for every electron that you remove from an atom, you increase the effective nuclear charge by about 0.35. And so a larger positive charge will mean a smaller radius. And you can see this pretty clearly if you compare some different charged ions. So the neutral sodium atom is going to have a size of about 190 picometers, whereas the cation is going to be 102 picometers. The magnesium atom is going to be 145 picometers, but the magnesium plus 2 ion is going to collapse all the way down to 72 picometers. So we see not only that the cations are smaller, but that the greater the charge on the cation, the smaller it's going to be. With aluminum, the plus 3 cation being 54 picometers, the smallest out of all of these cations, whereas the original aluminum was all the way up at 118. So there's a huge drop with that plus 3 cation because of the increase in the effective nuclear charge. There's another effect though to consider, and that is the fact that once you lose all of the valence electrons, you cause the external boundary of the atom to drop to the next energy level below it, right? How does that work? Well, let's consider this Bohr model for beryllium. If we go ahead and kick off one electron from beryllium, we go to a system, Be plus 1, which is going to have one valence electron now instead of two. But if we go ahead and then kick off the next valence electron to form beryllium plus 2, we remove the entire outside valence electron, and that boundary of that energy level for that atom just goes away. And so the atomic radius collapses all the way down to the next energy level. So we collapse from n equals 2 to n equals 1, which is a substantial collapse in radius. And so that's part of the reason that when we look at these atoms here on the left, the Na plus 1, Mg plus 2, and Al plus 3, why there's such a big drop in radius, because when we eliminate all of the electrons in that outside energy level, you're going to drop all the way back down to the previous energy level. So in this case, we're dropping from n equals 3 all the way back down to n equals 2. On the other hand, it will always be the case that anions are going to be larger than the neutral atom they come from. Why is that the case? Well, the increased electron repulsions in an anion due to the excess negative charge will make the electron cloud increase in size. In fact, you can calculate that the effective nuclear charge on an anion will roughly decrease about 0.35 for each extra electron that's added. So we can look at a chart here, and we see that the neutral fluorine atom, for example, is about 42 picometers, but the F- anion shoots all the way up to 133 picometers. Oxygen is about 48, but O2- is 140. And nitrogen goes from 56 to 146 when it's -3. Another thing to notice is just like the cations shrink the more charge accumulates, the more charge accumulates on an anion, the larger it gets. So the higher the charges, the more repulsions there are, and therefore the larger the anion will swell to. N3- is going to be larger than F-, even though they're isoelectronic. They have the same electron configuration, but because nitrogen has a lower effective nuclear charge with the same number of electrons, it's going to be much bigger, right? It's going to swell to a much larger size than the F-. A great way to visualize this is to compare the size of the cations and anions through an ionic bonded salt directly. And all of these that we're going to look at here are proportional to one another. So the sizes have been scaled so that they're accurate. So the first molecule is going to be sodium fluoride. So in this case, you see that the sodium cation is going to be smaller than the fluorine anion, but not that much, right? Fluorine is a small atom to begin with, and so the size increase of the anion and the size decrease of the cation isn't going to lead towards a huge discrepancy. And that's because these two ions are going to be isoelectronic with one another. However, if we go ahead and move towards NaCl, we see now a bigger discrepancy. The sodium cation is going to be appreciably smaller than the chlorine anion. If we go now to bromine, we see an even bigger discrepancy. Sodium is going to be much smaller than the bromine anion. And if we go all the way to iodine, the iodine anion is huge compared to that sodium cation. And these differences are going to impact the strength of the ionic bonding. They're going to impact the crystal lattice that these ionic compounds take, and different properties associated with them, such as melting points. So it's a very significant factor that we should consider, the atomic and ionic radii, that is. And with that, we've actually reached the end of the content for this video. Thank you guys so much for watching, and if you like what you saw, please like and subscribe to the channel. To learn more, watch our other videos in the chemistry playlists, and if you're looking to branch out to other subjects, check out our other science playlists as well. See you next time!